Good afternoon. My presentation today is titled Audio Restoration via Spectrogram Image Processing. The central question I want to answer is this. When an audio signal is corrupted by several different kinds of noise, should we clean it up with the classical one-dimensional filters we have been studying for weeks, or should we treat the time frequency restoration as two-dimensional image and use image processing tools instead? I will compare the two approaches head-to-head and show you the numbers. Here's the big idea in one slide. On the left, the situation we are all familiar with. A noisy audio waveform is a one-dimensional signal. So tools available to us are also one-dimensional, low-pass, high-pass, notch, all three kinds of noise. Broadband, periodic, and impulsive are mixed together in the one single dimension, which makes them hard to separate. On the right, the alternative, the short-time Fourier transform, maps that one-dimensional signal into a two-dimensional image with time on one axis and frequency on the other. And as we will see in the moment, the three noise types occupy generally different geometric support on the image. That distinction is exactly what unlocks the image processing toolbox. The STFT is our bridge between the two worlds. If we use the implementation from homework 1, a sliding Hamming window of 256 samples, hope of 128 for 50% overlap, and a 256-point FFT. At 8 kHz sample rate, that gives us about 16 milliseconds of time resolution and roughly 31 hertz of frequency resolution. Each pixel in the resulting image is the magnitude of the FFT at one time frequency cell plotted on a logarithmic scale in decibels. The important point is that this is exactly the same STFT function we are already built. We are simply looking at its output as an image rather than as a sequence of spectra. Now let me describe the test problem. The clean signal is a three-note melody, A4, C sharp, 5, E5. Each note sustained for a little over and 1 second, with a short envelope ramp at the edges. The total duration is 4 seconds at 8 kHz. Then I crop the signal with three quite different noise sources. First, additive white Gaussian noise at 5 decibel SNR, broadband. Second, a 1500 Hz pure tone, simulating electronic hum. And third, four single sample click impulses placed at random times. Look at the corrupted waveform at the bottom. In the time domain, the clicks are barely distinguishable from the noise floor. Everything is mixed together. So if you see the code, so there's only one MATLAB file. And if we start the code, then it makes clean audio and corrupted audio. So let me the sound. So this is the clean audio. This is corrupted audio. So let's see the STFT. The three musical tones become stepped horizontal stripes at 440, 554, and 659 Hz. The 1500 Hz hum is a single continuous horizontal line across the whole image, like this. And the clicks become vertical streaks because a single sample impulse contains energy at every frequency. So like this four yellow lines. This is the key inside, and the white Gaussian noise is the diffused green-yellow haze in the background. So this is the key inside of the whole project. In one-dimensional view, these noise overlap and are hard to separate. In two-dimensional view, they occupy different geometric supports, and image processing tools were invented precisely to handle objects with different geometric supports. Based on that insight, I built a 5-step image processing pipeline on the spectrogram. First, an intensity transformation. Flipping the log magnitude histogram to use full range, like the IMADjust operation from lecture 6. Second, a 1 by 1 9 median filter elongated across the time axis to wipe out the vertical click streaks. Third, a row suppression approach at 1500 Hz row, the two-dimensional analog of an IIR notch filter. Fourth, spectral subtraction with the per row noise floor. This is the operation that has no one-dimensional equivalent, and I'll spend an entire slide on it. And finally, a small Gaussian smoothing to clean up any remaining speckle. After all 5 steps, I recombine the clean magnitude with the original STFT phase and run an inverse STFT to get the audio back. So here's the sample pipeline visualized step by step on actual data. The corrupted spectrogram in panel A shows everything we described. After the median filter in panel B, the click streaks are gone. After row suppression in panel C, the 1500 Hz line is gone. After spectral subtraction in panel D, the background haze has dropped dramatically, and after Gaussian smoothing in panel E, the residual speckle is softened. Panel F shows the estimated per row noise floor that drives the spectral subtraction. Of all 5 steps, the one that generally cannot be done in one-dimensional is spectral subtraction. Let me explain why. The algorithm is simple. For each frequency row of the spectrogram, we take the 25th percentile of the magnitude values across time. Because the white Gaussian noise is approximately stationary with each frequency bin, while the signal is non-stationary. The melody starts and stops. The 25th percentile across the time is basically the noise level for that frequency. We then subtract this noise floor estimate from every cell in the row, with small over subtraction factor and a soft floor. Why is this impossible in one direction? Because a one-directional LTI filter applies same gain to frequency band across all time. Spectral subtraction, on the other hand, is a time-varying frequency-dependent gain, a different gain at every single time frequency cell. There is no LTI system that can do that. The trade-off in fairness is an artifact called musical noise, isolated leftover spectral peaks that sound like faint chirps. For a fair comparison, I built a conventional one-dimensional filter chain on the same corrupted signal, a length 5 median filter for the clicks, an IIR nodes at 1500 Hz with quality factor of 35, and a fourth-order Butterworth low pass at 1800 Hz to suppress broadband noise above the tones. This chain handles 2 of the 3 noises typed beautifully, but notice the fundamental limitation. The Butterworth low pass removes everything above 1800 Hz, but the broadband Gaussian noise that happens inside the signal passband survives completely untouched. This isn't a flaw, so let's compare two approaches. So I use the signal to noise ratio, defined exactly as in lecture. So 10 times the log base 10 of the clean signal energy divided by error energy. The error here is just clean minus restored, sample by sample. Two partial details. First, the 1D and 2D pipelines have slightly different group delays. So I align each restored signal to the clean reference by cross correlation before computing the error. Second, standard SNR is sensitive to amplitude, so I evaluated the SNR on unnormalized restored signal and applied the customary peak normalization when only writing the WAV files for listening. So here are the numbers. So okay. So this is the signal and FFT comparison. You can see the noise and the peak at 1500 Hz. This is the STFT for corrupted signal. And this is the signal processing. And this is the comparison for one-dimensional filter and two-dimensional filter signal. So you see the SNR value. So the corrupted audio sits at 1.99 decibel. The noise is essentially as loud as the signal. The classical one-dimensional filter chain brings up to 8.85 decibel, a solid 6.9 decibel improvement. And the two-dimensional image processing pipeline reaches 14.44 decibel. So you can see that the two-dimensional image processing filter was better than one-dimensional filter. So here's the visual confirmation in the spectral one domain. The bottom left panel, one-dimensional result. This shows the diffuse halo of the passband noise around the tones with these green areas. The bottom right panel, the two-dimensional result is visibly clearer overall, although you can see the faint patchy texture that I call musical noise. Before I conclude the comparison, the 2D approach means in passband noise, the 1D approach means on phase fidelity and on latency. It can be implemented sample by sample, while the 2D method has 60 milliseconds frame latency. They produce different artifact signatures. Neither approach is universally better. They suit for different applications. If you hear the restored noise, this is the one-dimensional filter restored noise. And this is the two-dimensional restored noise, the signal. So to wrap up, there are four takeaways. On representation, choose the toolbox. The STFC unlocks image processing tools that simply do not exist in one dimension. 2. Noise has geometry. Tones are horizontal lines, clicks are vertical lines. Broadband noise is haze, and each calls for a different image processing operation. 3. The real advantage comes from 2D native operations like spectral subtraction, which apply time-varying frequency-dependent gains that no 1D LTI filters can replicate. And 4. Every method has signature artifact. Pick up the trade-offs that fit your application. So thank you for listening.